Oh, go ahead. I'm here to listen.
Okay.
Thank you.
So for this evening, we're going to do two 6, 7, 3, 1, and 3, 2 sections and answer questions that come up. So I'm going to project some notes to go through. And let's get this back to showing. Okay, so you should see some notes here. And we're going to start with 2.6, equations with absolute value. So essentially, absolute value is the distance from a number to 0. So the absolute value of x is 5 is saying what has a distance? Of 5 from 0. And so on the number line, you can see 5 and -5. So x could equal -5 or 5. In other words, let's see. In other words, if you plug in the absolute value of -5, you get 5. And if you plug in 5 and you take the absolute value, you get 5, because the absolute value is the distance, and so the distance from -5 to 0 is 5, and the distance from 5 to 0 is 5. So that's why that works. Here we have something plus 2 has a distance of 5. And so that's a little bit different in terms of visualizing. This is x plus 2 then is 5 away, and this is x plus 2 is 5 away. And so we basically have x plus 2 could be -5, and x plus 2 could be +5. So essentially you drop the bars. One is the regular case, the other you make the opposite. I did the negative first just because it was on the left to right, but normally I would actually just drop the bars and put this one first and then that one. So solving, we get that x would be -7 and x would be 3. And you could check your work by plugging it back inside the original problem. And this is where some people make mistakes, is that they check but they don't go to the original. So you have to go back to the original. Absolute value, in this case -7 plus 2, does it equal 5? And yes, and then checking for 3 as our x value. So both those work. And then you can get even more complicated by creating expressions where you have 2 steps. So again, one is just drop the bars, the other one drop the bars and make it its opposite for one side. Typically the side that isn't the opposite is the easier side to make the opposite for. Solve for those. Subtracting 1, dividing by 2, subtracting 1, dividing by 2. And I'm happy to stop and show any of these steps, in between steps, if you need it. Just if you don't, I'm not going to take as much time because we're cramming an entire week's worth of lessons into an hour. So you want to make sure to isolate the absolute value portion of the equation before making your 2 cases, because you are going to see the absolute value can be these 2 things. So it needs to be isolated to have that meaning. When you do absolute value, you can also end up with extraneous solutions or fake solutions. Absolute values are always positive because it's a distance. The variable, though, can be positive or negative. So I wanted to show a couple special cases. So first off, we want to isolate this absolute value part. And so we're going to undo addition or subtraction first. Then undo this multiplication by dividing. Now that it's isolated, we make our 2 cases. Case 1, just drop the bars. Case 2, drop the bars and change one side to its opposite. And then solving from there, adding 1, dividing by 2, adding 1, dividing, oh, I said dividing by 2. I meant dividing by 3 gets you 2, and here dividing by 3 gets you -4/3. Let me move that down just a little bit more so we can see it. There we go. This one we would also isolate to start. And here it's saying this absolute value is equal to a negative. And the absolute value is always going to be positive. So this is no solution, we can tell from right here. However, if you don't realize that and you go ahead and you just kind of plug along and you solve it, subtracting 5, subtracting 5. When you go to check, again, with the original problem, you need to keep those absolute value bars, and you'll see right now 5 = 1, which is not true. And so this is an extraneous solution, or not a real solution. And with the -3, we also end up with a false statement. So it's quicker, of course, if you realize, oh, I've got an absolute value. It cannot equal a negative. So with absolute values, once it's isolated, I always think about, is it even possible? And if it's possible, then I continue on making my 2 cases and solving. So that's the equations. I have a few moments now. If you guys have any questions, well, Tiffany, it's just you right now. Do you have any questions on 2.6?
No, I don't.
Okay. So 2.7 is an extension on that. It's now inequalities involving absolute values. And so the only difference between solving an absolute value equation and an absolute value inequality, which is really the same thing between equation and inequality in general, even without absolute values, is that when you multiply or divide by a negative, you need to switch your inequality symbol. So when we do the inequality, there's lots of things that have a distance that is less than 3. So if I think about a number line, the distance being less than 3 from 0, I could go all the way out here. I can't go any further. And I can go all the way down here. That's a distance of 3 away, and I can't go any further. And I didn't want to have it equal, so I have those open dots. So with interval notation, smallest to biggest, open dots, so parentheses. In interval notation, x is less than 3, it's bigger than -3. In other words, when I use the less than in a compound like that, it can do the smallest and then the biggest. There is another way to do it, and that is to think of the 2 cases. So you can say x has to be less than 3 is case 1, and x, and when you multiply or divide by a negative, you switch your inequality symbol. So you switch your symbol and you make it a negative. So there are 2 changes for those absolute value, the negative, but also switching the inequality symbol. And it has to meet both of these 2 criteria. And there's a way that I like to remember that. If you have a great or greater than or equal to, great or, I'm kind of misspelling that so that you can see the word or versus less and less than. L-E, less than. And so that's the and. And so if I think about this, when I made my 2 cases, it was a less than, so it's going to be the and case. So it has to be this criteria and that. So if I were to go less than 3 and I were to go greater than -3, the and is the overlap. And so where they overlap is right there. And so from -3 to 3. So that would be your scratch work graph and your final graph. Or you can think about it conceptually and go straight there. So then if we think about it conceptually on this one, a distance being greater than 3, it means it's beyond the 3 and beyond the -3. And if we think about solving it, we would say x is greater than 3, great, or x is less than -3. So you need to have the word, you switch the symbol, and you take the opposite. And so if I were to graph x is greater than 3 and to graph x is less than -3, it meets either criteria. It's the union of the two. So it's this whole thing, so that it is not only my scratch work, but my final answer for the graph. For interval notation, -infinity to 3, union 3 to infinity. And with the inequality notation, you can write it just like that. You need to put the word or in to the computer.
Oh, so with those, we actually have to put the or in.
Yeah, because it means something different.
Or do we do the union?
If you're doing it as an inequality, use the word or. If you're doing interval notation, the union symbol.
Okay. I always get super confused on these ones. These ones are always kind of iffy to me.
Yeah, there's, I actually have a document I'm just going to project for you for a moment. Oops, that's upside down. So this kind of breaks down the 6 different cases for unions and intersections. So sometimes people think, oh, you know, okay, we're just opposing, so this would be, you know, the 2 separate sections, but when you're looking at the intersection, there actually is none. So sometimes people just make assumptions that what they graphed is their answer. So I really wanted to have like the work graph and then like final graph, so you can see that sometimes it's not a final graph. So here, for example, if we have x is less than some number a, united with something where x is greater than some other number b, when I unite them, merge them together, I have this disjoint section. And so then I'd use the union. But if I was asking for the intersection of those two, there is no place where they intersect. And so you'd have a blank graph, essentially. You can use the 0 with a slash through it or an empty set to show that. Other times when your inequalities are going the same direction, the union is from here on versus the intersection would be from the B on. And then similarly for if they're going in opposite directions for your inequalities, the union is everything that is graphed, and so it's everything, all real numbers, -infinity to infinity. And the intersection would be that section in between, and so it'd be between those 2 values. So there's 6 cases that can happen for inequalities, and you really need to pay attention to and versus or, you know, if it's a union or an intersection, and think about what that means in terms of merging the 2 together or looking at the intersection. Catherine, it's okay. Yeah, but I only gave her 2 ounces, so. Yeah. So the only difference with 4 and 5 here compared to the 2 and the 3 is that it has the equal sign. And so it would be a filled in dot. And so then you'd be using brackets. And then on this one, similarly, a bracket, a bracket. So do you have any questions on the interval notation of these?
Not really. I always get just confused, like with the union part, and like I feel, I don't know. I just get nervous when it comes to tests because like I understand it and I know it's obviously one of them, and I usually get it like on the first time. But every once in a while, I have to go back like, oh crud, this is what I did wrong. But
So
I think I'll be okay.
yeah, so basically the only time you use a bracket is for
when
the
it's
closed dot.
right? Okay. And this is honestly, like in the other classes that I've taken, has been what like I've had a problem with. It's not a big problem. I just little things.
Yeah, the hard thing about Math 80 is that there is so many little details that matter. So.
Yes, I've noticed that because I've taken 60 and then 220, and it's been fine. But it was the other one too, like 40 or something. But it's just these little things, like the little tiny things. I feel like I go too fast sometimes, which I'm glad that you require scratch paper because then I actually have to slow down and take my time.
Yeah, the scratch paper is just for tests, but I wouldn't be doing my homework without scratch paper either, obviously.
Yeah, no, for sure.
You just don't need to turn it in to me.
Yeah.
But if you have any questions, it's great to be able to like take a picture of your scratch work to submit along with your questions, so I can kind of see what you're thinking or where the trouble might be.
Yes, no problem. I didn't realize there was actually like a Tuesday question and answer kind of lesson thing, or else I definitely would have been.
Well,
there were a couple of things.
Go back if you want and see the week 2 one. Week 1 I didn't end up posting. I could go back and do that. It was
okay.
It was, I didn't realize the recording was not happening automatically being submitted.
Oh,
so
yeah. I did see, I think it was Thursday or Tuesday. I did see that there was a conference and I didn't know what it was. I saw it too late. It's like, oh, I wonder what that was.
Yeah.
She was trying to help us.
Yep.
Okay, no worries. Thank you.
So down here, I just thought I'd, these are my notes that I use for my on-ground class. So that's where they're coming from. It's not something you already have.
Oh, okay.
So the interval notation here, it's not really an interval. It's just 2 separate distinct points. And so you default to set notation. And then here you would say it's between -5 and 5. Sometimes they use parentheses. You saw it maybe in some of the videos, or they use an open circle. So it just depends on the book and the instructor, whether they use parentheses or brackets, or they use the open circle versus a closed circle. So there's that interval notation just to practice a little bit more.
Okay.
I find this to be, this is the formal definition that's in your textbook. But I find it to be a little bit intimidating with all the inequalities and all the ors and ands and thans, and
yeah,
a little intimidating. So basically what it's saying is that if when you make your 2 cases, if once it's isolated, you have a greater symbol, it's going to be the or case, this thing or that. Versus if you have a less than or less than or equal to, it's the and, it's the overlap. That's basically what that's saying, is that it's the or versus the and. So this is the and case, and this is the or case. And you can see there's the less than, and there's the great or. So you don't need to memorize the formal, just there is 2 cases, and if you think about it logically, like, okay, the distance is less than 3, so it's in between here, versus the distance is more than, so it's beyond. That can help, or the mnemonic device with a great or and the less than. So let's double check. I think I have a few more. Yeah, I do have a few more practice problems on the back of this. And I'm just going to project it so we can discuss it. So you can see it's already isolated, so I make my 2 cases, and we put the correct word in here, and it's a less than, so I have the and, so I'm going to be looking at the overlap. My second case, change the inequality symbol and switch it to the opposite, so -25. And then just solve like you would normally solve your algebra problem, and if you multiply or divide by a negative, you switch the inequality symbol. So once you've graphed, in this case, less than or equal to 9 and greater than or equal to negative 16, we're going to look for where are both of those being met, the overlap. And so it's just between negative 16 and 9. So again, scratch work, and then your final once you've looked at the and versus the or. Because had this been an or, it would have been everything when we join those two graphs together. So it makes a difference on your answers.
Okay, and the thing, when by the 16, the negative 16, do we turn it then? Because it looks like it's already, okay. Wait, no, that was.
We turn it when we make our second case.
Okay, I was looking and I was like, wait a minute. I know you turn it when it's a negative.
You turn it for your second case, and if you divide it by a negative, you might have to turn it again.
Okay. Gotcha.
So you'll see here when I isolate, when I made my two cases, that's when I changed it to a less than negative 12.
Okay, gotcha.
For the first case, you just drop the bars. It's the second case that you have these two changes.
This is a negative 12, yeah. Okay.
So you make your two changes on the equation portion, and you have to figure out how are they connected to each other, the and or the or. Those are the two tasks.
Okay, and then the and or the ors, are those going to be on the test? Are you allowed to tell us that?
Yes, because some of the questions are going to be, greater than.
Okay.
And some of them might be a less than, and then there may be some of each. So you might have an and you might have an or, you might have one of each.
Okay.
And you might even have like a special case like no solution, or the everything is a solution.
Okay.
As in like this case where when you graphed these two, if you're looking at the union, it would be everything. Or the intersection, and you're like, wait, there is no intersection.
Oh, okay. And then when we're doing that with the where there's no intersection, are we using the upside down union?
No, you
okay, when we write it like that?
The answer to the union of this is a blank graph. It's nothing. It's either this or sometimes we do like the empty set.
Oh, okay. I was just curious because I don't remember coming across the little upside down U. Like we didn't have to, I don't think we had to use it in any of the homework. So I was just curious.
I think it came up more, not in this situation, but when you were given like a set of values.
Okay.
Back in, let me see, I think it was.
Okay.
I think it was chapter 1. Actually, I think I have that right over here.
Okay.
Or else it's still coming up. Let me see. Where did I do that? That was. Okay, that was in 2.5 that we had some ors or some symbols. I don't know if there was a lot in the book or in the homework with the word or the symbol, but you should be comfortable with either situation.
Okay.
So.
Okay.
And there's that one with the set that I was mentioning. So let's go back though. That would be in the prior video if you want to go back and watch that.
Okay. And where do we find the videos? Is it like in files or somewhere?
I put it underneath the announcement from last week.
Okay.
And I also put it at the bottom of the module.
Okay. I didn't see it.
Let me see if I ended up hitting submit on that.
Okay.
I think I did. Yeah, office hours. Yeah, you'll see here, if you click here, it opens up the link to the YouTube session from last.
Oh, perfect. Okay.
Time. Yeah.
Oh, great. Okay, that's good to know. So I can't always, I was just home randomly, so I was like, oh, perfect.
Yeah, I try to put things in more than one spot so people can find it however they're thinking about it.
Great, thank you. I appreciate it.
All right, so let's get back to that. Okay. The textbook shows the whole idea of something being less than 3 away, or being more than. So they talk about it in terms of that conceptual, like, okay, the distance is less than, the distance is more than, and that's why we get those two cases with the word or here with the and, the conjunction. So you can either write it with the word and, I use the symbol this time, but write it with and, or you can do it as a compound inequality, because that means and.
Okay. Okay.
In which case, it's kind of nicer to solve those problems when it's like this. You can just add 5 to both sides and then divide by 2 on both sides instead of having.
Yes, I liked those ones. Those ones were nice. I like those problems a lot.
Yeah. It's just sometimes it's harder to initially set it up than to just drop the bars and make your 2 cases. But if you do the drop the bars and make your 2 cases, you have to make sure you realize it's an and you're looking for the overlap.
Okay.
All right, so then there's some special cases. Essentially, if you have an absolute value and you have an inequality, you have to be careful if you have it equal to a negative. So an absolute value is always positive. So positives are always positives are always greater than a negative. I should do this one first. Positives are always greater than a negative. And so if you have an absolute value that's greater than negative, it's all real numbers, negative infinity to infinity. And so instead of making your 2 cases and solving and checking your work and realizing everything has been graphed, you can do the shortcut of realizing, okay, it's all real numbers. Versus an absolute value is, because it's positive, it's never going to be smaller than a negative, right? Positives are never smaller than a negative. And so if you say, okay, this absolute value, this positive thing, can it be less than a negative? No. So then there's no solution. You'll see that if you do end up working it out and you check your work, here you're looking for where is it less than -9 and greater than -1, and the and is the overlap, and there is no overlap, so there's no solution. Let me zoom in a little bit more on that part there. That autofocus did not focus it very well. And then the other one, if you were to go ahead and work it out, your 2 cases, and it was a great OR for the original problem. So when you look at the when you look at it meeting one or the other, the merging, the OR, if you merge your 2 inequalities, less than 7, greater than 3, and you merge these together, it's everything. So those are the special cases, is when you have an absolute value and then you have a negative. Any questions on the homework or in general about 2.6 or 2.7?
No, I think I'm okay.
Yeah, so
I just have to work on all the little details.
Yeah, don't make assumptions, like actually work out the details. All right, so. All right, so now let's work on 3.1 and 3.2. And if you want additional practice, I think I put an additional practice into the into the Canvas. But if you want to see any worked out solutions to any of those, please feel free to message me and I can send you the worked out version. There are some special cases on it, so it forces you to really do the work and not make assumptions. All right, so 3.1. Let's see if I can't get this to focus again. Okay, so I'm not going to spend a lot of time on this, so just a quick review. X-axis, Y-axis. These are different quadrants. There's 4 quadrants, hence quadrant being used, quad meaning 4. Quadrant 1, 2, 3, 4. It's counterclockwise. It gets used in trig. You don't have to, worry about those particular terms right now. It's just a little introduction, but you should know the x-axis, y-axis, and origin. Ordered pairs are always the x coordinate, then the y coordinate. So it's how much you move right or left in the x direction. And then the y direction is the up-down direction. So positive moves you up, negative would move you down. So there's some practice on plotting points. For example, A is going to be at 6, 4. So I go 6 in the x direction, 4 in the y direction. This is the point 6, 4. And then I did the rest. So the thing to be cautious of is the ones with zeros. Sometimes people get that backwards. So like B here is 5 over 0 up. So it's 5, 0. Versus G here is 0, -4. So that should be a review from Math 46 or Math 60 Algebra 1 class. Oops, instead. Okay. To graph functions, to graph equations, if it's y equals mx plus b, there's a shortcut. But you can also always use a t-table, plug in x's, and get out your y's, and just do the arithmetic. And plot those points, and then make a line through them. You can also graph not only from a t-table, but by thinking about the intercepts. So getting 2 points by plugging in 0 for the y-coordinate to get the x-intercept, plugging in 0 for the x-coordinate, or sorry, for the x in the equation to get your y-intercept. So once you have those 2 points, you can then graph your line. So for example, here's an equation. This is in standard form. Plugging in 0 for y to get your x-intercept. 0 times anything is 0. Sometimes people just do the cover-up method. I think that's also shown in the video. And so then you get 3 for your x value when your y was set to 0. For your y-intercept, setting x equal to 0, finding your y value, you get 1. So once you have these 2 points for this line, you can graph them and draw your line through those 2 points. And if you want a few more points to make your graph a little more accurate, you just keep that same slope. Those lines have a consistent slope. So I go down 1 over 3, down 1 over 3. You go up 1 and left 3 as well. So that's kind of nice, except for sometimes intercepts are not nice integers like that, and so it can be a little bit more limiting. So in that case, thinking about y equals mx plus b can be helpful. Here's another one with x and y intercepts that's in the slope-intercept form. What's kind of nice is that when it's in slope-intercept form, that intercept is your y-intercept. If you do the math for it, you'll discover it is just that -6. The x-intercept can be a little bit trickier to find in these cases because you have a little more arithmetic to do. You have to isolate the x. But you'll see that it matches up with -6 as your y-intercept and a slope of 1/2. Rise 1, run 2. It looks like I'm only running 1, but that's because I have each tick mark is 2. And so this really is rise 1, run 2 because of the scale. So that's the intercepts in a t-table. But ultimately, we're going to want to be able to do this a lot quicker and having it in y equals mx plus b form, slope-intercept form, where you start with your y-intercept, you start at a point, and then you use your slope to get other points is the quickest. And so we'll see that in the next lesson more. So again, the names for these, that slope-intercept form is that y equals mx plus b. We saw one that was in standard form. That's some number x plus some number y equals some constant c. And then point slope is another way you can write an equation of a line, and you plug in the points, the x coordinate and the y coordinate here, and then you plug in the slope as your m. And then if there's, if you subtract a negative, you can simplify that to being a positive. We'll see that later. But really that's it. It's in a format that is acceptable for a line. So there's some special lines, like horizontal lines. We can see it with the t-table. We can see it by plotting points. This is y equals 3 because all the y values are 3. It goes through 3 on the y-axis. One way to remember this is a mnemonic device, OI VUX. OI is horizontal lines, have a slope of 0, so no steepness. You're rising 0 and you're running however much. 0 divided by anything is 0. And their equation is of the type y equals some number. Okay, no x's involved. Vertical lines, so here's the t-table. Vertical lines would have an x that's always something. So x is 2 in this case. And it has an undefined slope. So you rise however much, but you run 0. So you rise over run would be something over 0, which you can't divide by 0, so it's undefined. So vertical lines, undefined slope, and they have equations that are x equals some number. The last one that your book, the XYZ book, considers as kind of a special case are lines going through the origin. And that's when you do have an x and a y in this case. You do have a slope then. In this case 3, but the y-intercept isn't showing, and so it's kind of a little bit less comfortable because we don't see that plus 0 there, but that's what it is. It's plus 0. So you start at 0 as your y-intercept and you go up 3 over 1, up 3 over 1, or rise over run. And if you did a t-table, you get that. So t-tables are always a great default if you're not sure what kind of line it is, if it's horizontal, or if it's a vertical, or if it's going through the origin, or if it's just some other sloped line. So if there's just a y or just an x, those are the horizontal and vertical cases. Oh, looks like that's it for 3.1. Are there any questions that you have on 3.1 at this point? I have the formula for slope here, and another mnemonic device. Begin with your b, which is at the back of the equation, and then use your slope to move. M for move. It's not actually standing for that. So 3.2, just more review of slope. Positive slope goes uphill as you go to the right, you're going upward. Negative is if you're going downward as you go to the right. 0 slope means no steepness, so it's flat. It means slope is 0. Undefined slope is the one that's straight up and down vertically. It's that VUX case. If you think about rise over run, you'll realize you can't divide by 0, so that's the undefined. Sometimes people call it no slope. No is different than 0, and it can be a little bit confusing. I don't particularly like that phrasing. Undefined is definitely my preferred phrasing for that. It's less confusing. And then the slope formula that you probably have seen before, rise over run is y2 minus y1 over x2 minus x1. And that comes from, again, just thinking about the distance between your x coordinates, that's your run, and the distance between your y, that's your rise. And distance, you can determine that by finding the difference between the two coordinates, and difference is subtraction. So you can see why that works out. There's a little Mr. Slope guy or Mrs. Slope gal up here that some of my students have found helpful for the undefined nose, that vertical line, and the horizontal mouth with the little 0. And then a student said, well, you should have them saying way back, so I added that in. So that's just a little trick for some people if you find it helpful. So using the slope formula, I'm going to switch back to actually working some out. So find the slope of the line containing some points. So points are always x then y. This point is the first point, so I put a little subscript of 1. This is my second point, so I'm going to put a subscript of 2. So your slope is y2 minus y1 over x2 minus x1. Your rise is your y's. You're going to plug in your y1, your y2, sorry, y2, your y1, your x2, and your x1. So in this case, 6 minus 1, and then 5 minus 3. That doesn't reduce any further, so that's your answer. You don't have to worry about whether it's positive or negative. The formula will automatically do that as long as your second coordinates match up and your first coordinates match up. If all else fails, you can also plot those and count rise over run, and then simplify the fraction if necessary. So here we're going to have y2 minus y1 over x2 minus x1. So minus is part of the formula. So we can plug in, but we'll have minus as part of the formula and then a negative. So that's the same thing as saying negative 1 plus 3. And 4 divided by 2 does simplify to 2. So even though we normally think of slope as like rise over run, you'd still say 2. That's a simplified way of saying it, but when you go to graph, you would think, okay, 2 over invisible 1. So there's a few more just for practice. Essentially, it's practicing, that you're putting it in the right places, and practicing the double negative, practicing reducing, doing some work with, negative divided by negative is positive. Here, 6 divided by 2 is 3. 0 divided by anything is 0. If you're not sure if that's undefined or 0, make yourself a little graph and go, oh, that slope is 0. And here, 10 divided by 0. You can't divide by 0. It's undefined. But again, if you're like, is that 0 or is that undefined? Make yourself a little graph and go, oh, that's undefined. It's like the nose. Oops, I kind of drew that a little bit more mouth-like than I meant to. And then there are some questions in your homework where it starts involving variables and potentially even solving for variables. So there's questions similar to this where you just plug it in and you reduce it, and there's going to be a W in there because there's an unknown. It's just now a relationship between these points and the slope they would have. Here it says solving. So here's the equation that relates slope and a point and points, 2 points. Plug in what you know and then solve for what you don't know. So if 3 equals 8 minus k divided by 2, to get rid of division, you multiply. What you do to one side, you do to the other. Those 2's cancel. We have 6 equals 8 minus k now. Subtract the 8. Negative 2 is k. Equal to negative k. We don't want negative k. We want k. So we take the opposite of both sides, or divide both sides by negative 1. And then parallel lines and perpendicular lines. Parallel lines have the same slope, so you can put it in slope-intercept form. and steal the slope. These lines would be parallel. So to write an equation, there's two options. You can either have slope and a point and plug it into y equals mx plus b, because again, you have a slope and you have a point. Or you can plug it into point slope form, because you again have a point and a slope. When you plug into y equals mx plus b, you're going to have to find out the y-intercept of the b that would make this situation true, where it has a slope of 2 but goes through this point. So there's the point 2, 3. I wanted a slope of 2. What is the equation of that line? We didn't know what this is unless we graphed it and realized, oh, it goes straight through -1. Algebraically or analytically, here's the work. Or you can plug it into slope, point slope form. Put in the slope, put in the point, x and then y. And then you can either leave it like that, that's in point slope form, or if you distributed and got y by itself, you'd realize it is the exact same equation. So point slope form, slope intercept form. And it matches up. It does go through -1. Perpendicular, opposite reciprocal, so you take the opposite sign. So if it's positive, it becomes negative, negative becomes positive. And the reciprocal, so the numerator becomes the denominator, and the denominator becomes the numerator. So if you have a slope of -2/3, the perpendicular line slope would be opposite, so positive, reciprocal, so 3/2. Or if it was 5, opposite would be negative, reciprocal, 5 is really 5/1, so it's going to be 1/5. So you can be asked all sorts of questions about parallel, perpendicular, neither. Either just are they parallel, perpendicular, neither. What is an equation that would have that would be parallel or perpendicular? What would the slope be? You could be asked to write an equation. You could be asked, do these two lines have these points on them? End up being parallel, perpendicular, or neither. So there's different situations, and you'll see that in your homework. So find the slope, and see if they are opposite reciprocals. For perpendicular, see if they're the same for parallel, or if they're neither. In this case, they were the same, so parallel. So we're going to take the, find the equation for a line perpendicular to this. So we're going to take the opposite reciprocal slope of this. So the slope for the perpendicular would be -3/2, and we want it to go through this point. So this is the information we have, and we're going to write the equation for this information. Again, either into y equals mx plus b, or into y minus y1 equals mx minus x1 point slope. And then if we graph it, just to confirm it, it does end up looking like that perpendicular 90-degree angle. So it's a nice confirmation. And I believe that is that for that lesson. We've got about 10 minutes left. Are there any questions that you have?
Not right now. I'm gonna go back and look at the perpendicular stuff, or perpendicular or parallel stuff again. I always have kind of I get kind of confused on that when I'm doing like the problem, like the whole thing. Like it's just always kind of funny to me. I'm not sure like what I'm doing wrong, I guess.
Okay, do you want to work through another problem together maybe? I think the perpendicular one really kind of would help you even with the parallel. Are you referring to problems like, let me get this back up here. Oops. So if you have a problem like y equals 2/3 x plus 7. 1, 2, 3, 4, 5, 6, 7, up 2 over 3, or down 2, left 3, I'll make 3 there. Let's say I have that line, and I want to figure out an equation of a line that is perpendicular to that goes through the point 8, 1. 1, 2, 3, 4, 5, 6, 7, 8, 1. So essentially what I'm trying to do is figure out, going at a 90-degree angle here as best I can, you know, where would that cross? So I'd have the slope and I'd have the y-intercept. So where does it cross? And you know, if you don't pick a nice point, it can cross at a fraction. If you pick a nice point, it can cross right at a nice integer, and you can tell from graphing what it would be. So we want to do perpendicular to this through that point. So we have the slope for the perpendicular would be the opposite reciprocal. And looking at this, you can see maybe that that the slope is down 3 right, down 3 right 2. It's a little bit tricky to see on a sketch like this. And again, the point is here, so that's our point. And so to write the equation, are you familiar enough with the point slope one, the one right here? Or is that new to you?
No, it looks familiar.
Okay, so I'll show it both ways because it's good practice, especially as you move on in math, to be comfortable with both. So if you plug it in here, you have a y equals your m, and we're doing the perpendicular, so I'll put a little perpendicular sign in here. So we're going to find it that has a slope of -3/2. And oops, I want an x of 8, and I wanted a y of 1. That's not unknown. I actually have the y value. But we need to figure out what's the y-intercept to write the equation. Cross canceling, -12 plus b. So I now have my slope of this line that's perpendicular. The slope is -3/2. And I have my y-intercept as 13. So it's about stealing the opposite reciprocal for perpendicular and the point, plugging it in, and solving for the unknown. So y minus y1 is 1. The m that's for our line that's perpendicular would be -3/2. And literally you can leave it like that and have it be just in point slope form. Or if you wanted, you could take it from that format, distribute. Negative times negative is positive. 24 divided by, so 8 times 3 is 24, divided by 2 is 12. And then get your y by itself. And you can see that those match up. So it's the same equation, it's just 2 different formats.
Okay, gotcha. And so then the -3x plus 13 is the line that will.
So this would have gone through.
They'll intersect on.
Yeah, I mean, as I said, this is a sketch. It was really not very well done to scale.
Oh no, that's fine.
It would have crossed through 13 had I graphed it better. And that's the reason why, you know, doing the arithmetic is also good, because our sketch would have been not the best. Even if I had graph paper, you know, since it landed right at 13, that would have been great. But if I had made this like 9-1, it would not have gone through a nice integer, and so you would have just been going like, well, it's near 9, but you wouldn't know if it, you know, what it should actually be.
Yeah, no, it's super easy I understand it a little better now compared to before. I'm trying to find like what number it is, or I'm like, I don't know what's going on. But it's nice to have like the little formulas.
Yeah,
that makes it a little easier to work with. I'll have to go back and rework it, and so I understand it a lot better. But I do feel a little better having the formulas.
Yeah, so it's if you're writing the equation, you want it in one of those two formats. You can't get it straight into standard, so you either have one of those two, and you plug in what you know and solve for what you don't. In this case, there's no solving for what you don't know. You know everything. That's the beauty of point slope when you're given a point and a slope. One thing that people sometimes don't do correctly is that they do the original slope. They don't take the perpendiculars. So they would have kept this as 2/3 and then had the wrong answer. So you want to work it with the perpendicular slope because you're trying to find it going through that point and having the perpendicular slope. All right.
Okay, perfect.
So there's plenty of more examples in the Canvas lesson too of writing equations, but it is something moving forward you want to be comfortable with is writing equations for lines.
Okay, sounds good. Thank you.
All right, have a good night.
All right, thank you so much. Have a good night. Bye.
Bye.